Let us see array implementation of Q data structure. We need to implement these operations, NQ, DQ, and these additional operations. Let's understand the working of these operations with an example. Let's say we initially have an empty queue. When we insert the first item, it becomes both front and rear. So 10 is your both front and rear. Now when you insert 20, you always insert an item at the end of current rear and make the newly inserted item as rear. So after the current rear, we insert 20 and make it rear. Now when you call NQ again, you always insert after the current rear and make it new rear. So you insert 30 here and make it rear. When you remove an item or when you call DQ on Q, you remove the current front and make the next item of it as your new front. So when you call DQ on this, you are going to remove this 10 and you are going to make this as front of the queue. So this is your Q data structure after calling DQ. Now there are some additional operations that we need to implement. One is size, that tells you how many elements are currently there in the queue. For example, if you call size at this point, you will get the output as 3. One operation front, when you call get front, you should get 10. When you call get front here at this moment, if you call get front at this moment, you should get 20. Get rear, it should give you the rear at any moment. If you call get rear at this moment, you will get 30. If you call get rear at this moment, you will again get 30. Is full tells you if the queue is full. Now what do we mean by queue full? See, we are using an array implementation and you have a capacity and size. You pre-allocate some space and then you insert the elements in the queue. So while you are inserting the elements, your capacity may become full. Your size may become equal to the capacity. When that happens, we say the queue is full. And what is empty? When your array is empty or queue is empty. So our queue was initially empty. Now if we call DQ 2 more times, it will again become empty. So is empty should return true. If our queue is empty, it should return false if the queue is not empty. Now please pause this video and try to implement queue using array. Let us first talk about the simple implementation. In this implementation, our NQ operation is going to be big O of 1, but our DQ operation is going to be big O of n, where n is size of the queue. Then we will talk about an efficient implementation where we will have both NQ and DQ in big O of 1 time. So the idea that we are going to follow in this simple implementation is we are always going to maintain front at index 0 and rear at index size -1. And if the queue is empty, then front and rear are undefined. We can return probably -1 when somebody calls get front and get rear for an empty queue. Otherwise, we return index of the front item and index of the rear item. And index of the front item is always going to be 0 if there are items in this simple implementation. And index of the rear is always going to be size -1 if there are items in this simple implementation. When we talk about an efficient implementation, we will not have these constraints that front is always 0 and rear is always size -1. But let's focus on the simple implementation for now. So what we do is, when we add an item to this empty queue, we always add it to the front. And when you insert the front item, your both front and rear become 0. Now when you add 2 more items, 20 and 30, your front remains 0 but rear becomes 2 because this is your new rear, right? You always inserted the rear and size becomes 3. Now when you DQ an item, you want to remove 10. So what you do is you move the remaining items, n-1 items, 1 position back, right? So your 20 comes here and 30 comes here. So when you are DQing, you are actually moving n-1 elements or size -1 elements. That's why DQ is big O of n operation. But NQ is simple. We simply need to do rear ++ and insert the item at the rear. So these are the structures that we are going to follow in Q. This is the class in Java and this is the structure for Q in C++. We need to follow these structures in this simple implementation. And we are going to have size and capacity. Size is current size. Capacity is provided by the user that defines how many elements are going to be there in the array. What is the size of array? We pass it as a parameter to the constructor. Then we allocate an array of that size, right? Of the capacity. I have used ... dots in the functions. You need to implement these functions. And if you're programming in Java, then you need to implement the same functions in Java. The class of Java is also similar. We have an array. We decide the size of array and number of elements in the array. And we also allocate memory for this array in the constructor. Now please pause this video and try to write down all these functions in this simple implementation. Let's now see the implementations of the required functions. The code written here is some sort of pseudo code which is close to both C++ and Java. Only minor changes are required. For example, if you're programming in Java, then you need to replace this bool with boolean. Let's now see the working. Here in this implementation, we are following the same structure in C++ and same class in Java. We are going to maintain size and capacity. We are not maintaining separate variables for front and rear. Front is always 0 if there are elements, and rear is always size minus 1. And you can take a look at these functions. Get front function, if the queue is empty, it returns -1, otherwise it returns 0. Index of the first element, always front is 0. Get rear function, if queue is empty, then it returns -1, otherwise it returns the index of the rear, which is always size -1. Let's now see the implementations of these functions. So enqueue function, it simply adds an item at the end. So if there are currently size items and if indexes begin with 0, that's how indexes are in C++ and Java, then your element is going to be inserted at that size, and then you're going to do size ++, right? That's how it is inserted in the end. Dequeue is slightly complex. It is taking big O of n time. The reason is we want to maintain front at index 0. Now, so what we do in dequeue operation, when we want to delete an item, we want to delete from the front. So we are going to move all the items starting from the second item to one index back, right? So we are moving array 1 to array 0, array 2 to array 1, and so on. And we run this loop from 0 to size -2, right? So we create an extra space at the end, and after doing this movement, we do size -. Let's see the working with an example. So this is our queue, right? And we want to dequeue an item. So what are we going to do? We are going to move this 20 to 10, 30 to this position where 20 is, and 40 to the position where 30 is. That's what we want, right? After we do dequeue. So that's what this loop does. And after you executed this loop, your array will be modified to this. We have two more functions, isFull and isEmpty, which are really simple. IsFull function simply checks if size is equal to capacity, then it returns true, otherwise false. And isEmpty function returns true if size is 0. In this implementation, time complexities of all the operations are big O of 1. There's only one operation which is big O of n. Now please pause this video and think of an implementation where time complexities of all the operations are big O of 1. Let us now talk about the efficient implementation. The idea is to use circular array. With circular array, our all operations become big O of 1 and we do not waste any space in the array. Let's see this example to understand. We have an array of size 4, which means capacity is 4 and size is also 4. And front is 0 and rear is 3. Now, if we wish to remove an item, if we wish to dequeue an item, what we do is we simply do front equal to front plus 1 modulo capacity, right? So we increment the front in circular way. So we remove 10 and front comes here. Now we again want to dequeue. We'll again increment front in circular way. So front will come to index 2, right? Now if we want to enqueue an item, and this is where you will actually see a circular implementation use. If you do not use circular implementation, what will happen? You will not be able to insert 50 because there is no space after it, although you have space in the array. But if you increment rear under modulo capacity, you can increment rear to this point, right? And you can insert 50 here. So we do rear equal to rear plus 1 modulo capacity, and that's how we get the rear as 0, because currently rear is 3, and if you do 3 plus 1 mod 4, you get 0, right? So your rear comes here and you insert the new item here. Now if you delete an item again, 30 will go away and front will come here. Now if you delete 40, then front will also come here. That's because front is also incremented in circular way, right? So with circular implementation, all operations are big O of 1 and you are not wasting any array space. Now please pause this video again and try to write down a complete code to implement circular implementation. Here is a hint for circular implementation. This is C++ structure that we are going to follow in the efficient implementation, and this is Java class that we are going to follow. You can notice that here is a difference from the previous implementation. Here we are maintaining front also with size and capacity, right? We have front, capacity and size. And we are not maintaining rear. because we can always get the rear as front plus size minus 1 modulo capacity. For example, if you see this here, your size is 4 and front is 0, you can get the rear as 0 plus 4 minus 1 modulo capacity, which is 3, right? If you see this example again, you can get the rear using this formula, this particular formula, right? You can notice in all the examples here, we can get the rear, especially this is interesting. Front is 2 here, this is index 0, this is 1, this is 2, and rear is at index 0. So we can get the rear as 2 plus size is 3, 2 plus 3 minus 1 modulo 4, which is 5 minus 1, 4 modulo 4, which is 0, and your rear is 0. So this condition always holds in this circular implementation. This should hold because front is floating, it can be at any point, but it is moving in circular way. So all the elements after front are contiguous, right, and in circular way. So if you apply this formula, you will get the last index in circular array, which is rear. So this is the idea for implementation. We are maintaining front with size and capacity because front can be anywhere in the array. It does not have to be at index 0 like simple implementation. And these statements should give you pretty much idea. Now please pause this video again and try to write down all the functions. Let us now see the implementation. This is done in a pseudocode which is close to C++ and Java codes. There are only minor changes. For example, if you're programming in Java, you need to replace this bool and this bool with boolean. So the idea is same that we just discussed. We maintain 3 members in our class: front, size, and capacity. And we get the rear using this formula. You can take a look at this get rear. We follow the formula front plus size minus 1 modulo capacity. And our get front function is simple. If it's empty, then return minus 1, as simply return the front index. Now is full and is empty are same as simple implementation. If capacity and size are same, then return true, otherwise return false. Is empty is also same. If size is 0, then return true, otherwise return false. Now let's see the enqueue function. Enqueue function first checks, you're trying to add an item to the queue, so you should be checking whether the queue is full or not. If queue is full, then we return. Otherwise, we get the rear. So rear is not part of the class. We get it using this function, which gives us this. And once we get the rear, we do rear equal to rear plus 1 modulo capacity, and we do size plus plus, right? In dequeue, we again do the same thing. If queue is empty, if you're trying to remove an item from a queue which does not contain anything, you should return. Otherwise, front equal to front plus 1 modulo capacity and size minus minus. Let's now see the working of these functions. Initially, our queue is empty. Then we did enqueue10. So when you do enqueue10, what happens? You get the rear using get rear function. And in the constructor, we initialized front as 0. So how do you get the rear? You do front plus size minus 1 modulo capacity. So we'll get 0 plus 0 minus 1 mod capacity. So we'll get the rear as minus 1. And after we get the rear as minus 1, we do rear equal to rear plus 1 modulo capacity. So our rear will become 0. So we'll insert the 10 at index 0 here at this index. Now when you do enqueue20, what you will do? You will again get the rear using this formula. And what you will get now? Your front is still 0 and your size is now 1. So you will get 0 plus 1 minus 1's capacity, which means 0. So you will get 0 here. And then you will get the next index as 0 plus 1 modulo capacity. So you will insert 20 at index 1. Similarly, when you are inserting 30, you will insert 30 at index 2 using the same process. Now, if you do a dequeue, say you do the first dequeue, what will happen? In the dequeue operation, you will do front equal to front plus 1 modulo capacity. So your front will come here, right, after the first dequeue. And after doing the next dequeue, your front will come here at 30, right, which is index 2, right? That's what happens after 2 dequeues, and your size also reduces after every dequeue. Now, if you do enqueue40, you will again follow the same process. Your front is at 2 and size is now 1. Now, if you want to add an item, you will get the rear, and what you will get as a rear? You will get the rear as 2 plus 1 minus 1 mod 3. This is capacity. So you will get the rear as 2. So you get the rear as 2. And then you do rear plus 1 mod capacity. So 2 plus 1 mod capacity, you will get the rear as 0. So you will insert this at index 0. And this is how this enqueue40 happens. Then you do dequeue. So when you do dequeue, you will again simply do front equal to front plus 1 mod capacity. So your front will now become 0. So front and rear both are 0. See, rear is not maintained as a separate variable. Rear is always this. So you can get the rear as well. So your rear will be 0 plus size 1 minus 1 0 mod capacity. So rear is also 0 at this point. So this is how all these functions work. All of them have time complexity big O of 1 and they do not waste any space in the array. If there is an item space in the array, then the item will be inserted in the queue.